Welcome to this explainer. Today, we're jumping right into the absolute ultimate forensic toolkit for chemists, IR and NMR spectroscopy. You know, have you ever actually stopped to wonder how scientists figure out what a newly discovered molecule looks like?
Think about it. Molecules are the invisible suspects of our microscopic world. So how do we know what they're made of when they are literally far too small to see? I mean, we can't exactly put them under a standard magnifying glass, and we definitely can't just snap a picture of them with a camera. We're dealing with structures on the nanometer scale here. So we need a completely different, highly specialized way to interrogate them and force them to reveal their secrets.
The answer to that mystery is spectroscopy. It's this brilliant forensic science that uses light to see how molecules absorb energy and undergo specific, measurable transitions. Basically, when we hit matter with electromagnetic radiation, we're fingerprinting molecules using light. Different types of light make the molecule react in totally different ways. And those transitions, how they react, how they move, how they absorb that energy, well, they tell us an incredible, highly detailed story about their structure, their bonding, and their whole chemical environment.
So, let's open up the detective's notepad for today's investigation. We're going to cover the molecular mystery, IR, the functional fingerprint, NMR, mapping the structure, comparing the toolkit, and finally, solving the case.
Starting off with Section 1, the molecular mystery. Because, to solve any chemical puzzle, you've got to figure out exactly what specific pieces are scattered in front of you before you can even begin to build that final picture.
Let's dive right into Section 2, IR, the functional fingerprint. This is our first big investigative tool, infrared spectroscopy, or just IR. It's the technique that identifies exactly who is present at the scene by sniffing out the functional groups of a molecule. It's a beautifully elegant process, really, just a rapid cause and effect chain. First, infrared radiation, which is just a specific band of light, gets passed straight through our chemical sample. Next, specific chemical bonds inside that sample act kind of like tiny antennas, absorbing very specific, highly targeted frequencies of that light. Then comes the magic. That newly absorbed energy physically causes those exact bonds to undergo stretching and bending vibrations. They literally start moving. Finally, a detector reads which frequencies of light were absorbed and which pass through, giving us a unique spectrum. We are taking invisible physical movements and turning them into a 2D graph that we can actually read. How cool is that?
Now, when we say these bonds vibrate, they actually perform quite the microscopic dance routine. Chemical bonds aren't rigid little sticks. They behave a lot more like flexible springs. And I find it endlessly amusing that chemists use highly technical terms like wagging and scissoring to describe this. Bonds can stretch symmetrically, pulling apart together, or unevenly in an asymmetric way. They can bend by rocking back and forth, twisting out of plane, or scissoring toward each other exactly like a pair of shears. Every single one of these distinct movements requires a different amount of energy, which means they each absorb a slightly different frequency of infrared light.
And we can definitively map those tiny dance moves to specific regions on our graph. In an IR spectrum, the x-axis measures the wave number, and higher wave number simply means higher energy. The whole region from 4,000 down to 1,500, that's our functional group detector. If you spot a broad OH peak around 3,200 to 3,600, boom, you immediately know an alcohol group is there. Or take the carbon double bond oxygen. A deep, strong peak at exactly 1,700 is a dead giveaway for a carbonyl group. Now, everything below 1,500 is called the fingerprint region. It's a highly complex, overlapping mess of bending vibrations that is entirely unique to the whole molecule, literally just like a human thumbprint.
IR is an amazing tool. It's incredibly fast, totally non-destructive, and modern Fourier transform instruments give highly accurate results in seconds with almost zero sample prep. But hey, a good detective knows the limitations of their tools, right? Sometimes those overlapping peaks can cause some serious confusion. And ultimately, IR cannot determine the full structure on its own. It absolutely tells us what the pieces are, but not how they actually fit together.
Which brings us to Section 3, NMR, mapping the structure. Let's see how we solve that exact structural problem using nuclear magnetic resonance, or NMR for short.
NMR fundamentally changes our tactic here. We move from molecular vibration to nuclear spin. We're relying on the really fascinating fact that specific atomic nuclei, like hydrogen-1 and carbon-13, basically behave like tiny magnets. When we drop our molecule into a massively strong external magnetic field, all these tiny atomic magnets are forced to align. We then hit them with a pulse of radio waves, giving them just enough energy to flip against the field. When the radio waves turn off,
The nuclei relax back to their original state and emit their own radio signals. Those emitted signals tell us exactly how the molecule is wired together from the inside out. We measure these emitted signals as chemical shifts in parts per million, or ppm. This is basically your decoder ring for the molecule's electronic environment. Think of the electrons orbiting the nucleus as a protective shield against that giant external magnet. Highly shielded nuclei, the ones insulated by a thick cloud of electrons, appear upfield at a lower ppm, right near 0.9 for simple alkanes. But de-shielded nuclei, where nearby atoms like oxygen greedily pull electrons away, while they leave the nucleus exposed to the magnet, these de-shielded protons appear far downfield at a higher ppm. So finding a signal way downfield at 10 to 12 ppm tells you right away that you're looking at a highly de-shielded carboxylic acid proton.
Okay, now we arrive at what is arguably the most crucial concept you absolutely must understand, the N+1 rule for spin-spin splitting. A signal in an NMR spectrum doesn't always show up as just one single peak. It actively splits based on its neighbors. Why? Because those neighboring protons are also tiny magnets. The proton we're observing feels the giant external magnetic field, sure, but it also feels the tiny magnetic fields of the protons right next door, which slightly alters its environment. The rule says a signal splits into a number of peaks equal to the number of adjacent hydrogens, that's your N+1. If a proton has two adjacent neighbors, those neighbors create three possible magnetic combinations, so the signal splits into three distinct peaks. It's a literal structural map, letting us count the exact neighbors in the carbon skeleton.
So NMR is undeniably powerful stuff. It's heavily relied upon all over the globe for figuring out complete molecular structures and pushing drug discovery forward. Actually, fun fact, the exact same magnetic resonance principle is what powers medical MRIs in hospitals. Because of its incredible detail, it gives us quantitative, totally non-destructive analysis. But it's not perfect. It demands highly pure samples, complex interpretation, and honestly, we just have to stand in awe of the extremely expensive, liquid helium-cooled superconducting magnets required to even run the machine.
Moving to Section 4, Comparing the Toolkit. Let's bring our lineup of evidence together and see how these two methods play off each other.
When you put them side by side, it perfectly captures why you absolutely need both tools in your forensic arsenal. IR is entirely about molecular vibration. It uses infrared radiation to quickly output absorption peaks that identify specific functional groups. NMR is completely different. It's based on nuclear spin behavior using radio frequencies to output chemical shifts that reveal the full, deeply detailed molecular structure. So IR gives you the quick functional fingerprint, while NMR maps out the detailed interconnected blueprint.
And finally, Section 5, Solving the Case. With our toolkit fully explored and the science decoded, let's wrap this up with some actionable advice.
Look, if you want to master this toolkit and absolutely ace your chemistry exams, here are your precise marching orders. You've got to memorize those key IR absorption ranges and NMR chemical shift ranges cold. Literally physically draw out your molecular diagrams so you truly understand those N+1 splitting patterns. And most importantly, practice solving unknown spectrum problems regularly. Reading spectra is exactly like learning a new language. You can't learn it just by staring at a dictionary. You need constant repetition and immersion, so your eye just naturally catches those tiny molecular clues.
I love this quote directly from the source material. Think of spectroscopy like solving a mystery. IR tells you what groups are present, NMR tells you how everything is connected. It really just brilliantly summarizes today's entire explainer, perfectly linking the who with the how for a complete airtight investigation. So now that you've got the rapid fingerprinting power of IR and the profound structural mapping of NMR, you've essentially unlocked a brand new way of seeing the invisible world. You can read molecules like a language. So the only question left is, what microscopic mysteries will you uncover next? Could you be the one to map the exact structure of tomorrow's next big life-saving medicine? Keep analyzing, keep practicing those spectra, and I'll catch you on the next explainer.